In this lesson, we're going to be looking at exponential models, so we're going to write equations, and then we'll use those equations to solve problems. In example 1, we're going to write a function rule for each relationship that's described. So in 1a, we have a landfill that initially contains 5,000 tons of waste and accumulates an additional 410 tons of waste each month. So we're going to make a table of values, and we need two variables here. The thing that we're measuring is the amount of waste. Let's call that W. Let's be really specific about it. It is the number of tons of waste. And then we're measuring this over time. So T is going to be our input variable, and T will be the time in months since that initial time. So T, the input variable, goes in that first column, and W, the thing that we're measuring, goes in the second column since it's our output variable. Think of time as a stopwatch that starts at 0. So our initial time will always be 0. And at T equals 0, there are initially 5,000 tons of waste. After 1 month, there are 5,410 months, but I want you to think about how we got that 5,410. We take the initial 5,000 tons of waste and add an additional 410 to it. In fact, the word additional really comes from adding. At the end of 2 months, we have our initial 5,000 tons of waste, but we've added on 410 twice, or we've added 410 times 2. At the end of 3 months, 5,000 plus 410 times 3. Let's backtrack and write in some values that are really assumed. For instance, when T is equal to 1, that 410 gets multiplied by 1. And when T is equal to 0, we're really adding 410 times 0. What I want you to notice here is that the 5,000 is the same in each row's entry. The 410 is the same in each row's entry, but that multiplier on the 410 changes from entry to entry. So if T is a variable, let's put a T in that column, then the amount of waste is 5,000, that's the same in every row, plus 410, also the same in every row, but the multiplier on 410 is the same as the T value. So now when we write our equation, you can see that W is equal to 5,000 plus 410 times T. So that is our equation. And you can also observe here that that's a linear function. That is, our slope here is 410 and our intercept is 5,000. In B, we have a small town that has an initial population of 30,000. So let's make a table here and let's define some variables. P is the number in the population, and T is the number of years since that initial time. So T is our input variable. The thing that we're measuring is population, so that goes in the output variable column. And our initial time is 0. At that initial time, the population is 30,000. Now, again, I know that when 1 year passes, we'll have 60,000 people in that town. However, I want to think about how we got there. Doubling means that we're multiplying that amount by 2. At the end of another year, we'll double again. So that's times 2 times 2, or times 2 squared. At the end of 3 years, multiply by one more factor of 2. That'll give us a 2 raised to the third power. So at the end of T years, let's go back and fill in some assumed values here. It would be safe to say that in the row where T is equal to 1, the exponent on 2 is 1. And in the row where T is equal to 0, the exponent on 2 is 0, since 2 to the 0 is 1. And so that would give us 30,000 times 1. Doesn't really change the value. So when t is a variable, then p would be 30,000 times 2 raised to the t power, since you'll notice that when t is 3, the exponent is 3. When t is 2, the exponent is 2. When t is 1, the exponent is 1. And when t is 0, the exponent is 0. So our equation is p, the population, equals 30,000 times 2 raised to the t power. And you can use that exponent around the 2 if you wish. Not necessary. We'll use that parentheses around the 2 if you have a fractional value there, but if it's a whole number, it's not necessary. All right, so let's contrast these two situations. In A, we had a function, the amount of waste, that was increasing by a constant rate, 410 every month. That turned out to be a linear type of a function. And in B, we had a function, the population, that increased by a constant factor, that it was multiplied by 2. Now it could decrease by a constant factor, that is, be multiplied by a fraction. Either way, this is going to turn into what we call an exponential function. And you recognize exponential functions because they have the variable in the exponent. All right, let's take a look at a couple other problem situations and we'll add a layer of complexity to this. So in example 2a, we have the number of bacteria in a culture at the start of an experiment is 300. They give us some variables to use here. They said that t is time measured in years and n is the number of bacteria. So we can already go ahead and fill in our initial time, 0, and our initial number of bacteria is 300. However, in this situation, the doubling happens every 5 years. So that means our next data point is when t is equal to 5, the number of bacteria in that culture will have multiplied by 2. After another 5 years, so at t equals 10, that number would be multiplied by 2 once again. And at t equals 15, or another 5 years, that number will be multiplied by 2 again. Let's fill in some assumed values here. The exponent on the 2 in the second row is 1, and in the first row here, the exponent on the 2 should be 0. So if t is a variable, then the number of bacteria is 300 times 2 raised to the, and this one's just a little bit more complicated. When t is 15, the exponent is 3. When t is 10, the exponent is 2. When t is 5, the exponent is 1. And when t is 0, the exponent is 0. So what you'll notice is that the exponent is a factor of 5 smaller than the time value. So the exponent is the time value divided by 5. So when we write our equation, it will be n, the number of bacteria, equals 300 times 2 raised to the t over 5 power. All right, let's take a look at a half-life problem. You'll remember these from chemistry. There are initially 500 grams of a radioactive material present. They give us variables here. A is the amount of radioactive material. T is our input value, or time, measured in hours. So after 0 hours pass, that's our initial time, so that means we have initial amount of 500 grams of that radioactive material present. After 1 half-life passes, so after 7 hours, we have half that amount. So you can find half of an amount in a couple of different ways. You can divide by 2, but it's going to be better for us probably to write this as times 1/2. After a second half-life, so after another 7 years, t equals 14, the amount gets multiplied by 1/2 again. and at t equals 21, or after 3 half-lives, the amount gets multiplied by 1/2 again. So if t is a variable, then the amount is 500 times 1/2 to the, and now let's figure out what's happening with our exponent. When t is 21, the exponent is 3. When t is 14, the exponent is 2. When t is 7, our exponent is 1. And when t is 0, our exponent is 0. So you'll notice that the exponents are a factor of 7 smaller than the value of t. So that means that the amount is 500 times 1/2 to the t over 7. Since we have a fractional base, it is important that you write the parentheses around that 1/2. Otherwise, it looks like only the 1 is being raised to the t over 7 power. All right, in C, we have an investment problem. And in this one, the investment pays a whopping 6% annual interest rate. I put in that descriptor because current interest rates are very, very low. So 6% is a very large interest rate. If you find an investment that pays that, like a savings account, I would put my money in there. But for purposes of this, we're just going to use 6% because it makes the numbers a little bit easier to work with. So we have $2,000 invested initially. Just so there's no further complications, we're not going to make any withdrawals or additions to the account during the investment period other than the interest. We're going to write an equation that models the relationship between V, the value of the investment, so that sounds like an output variable, and T, the time measured in years. Now the hint here says be careful with this distinction between months and years. So let's go ahead and enter an initial amount. When T is 0, the value of the investment is 2,000. That's the easy part. All right, now let's pay attention to what it means to say that we're compounding the interest monthly. Notice that 6% is our annual interest rate. That means this investment pays 6% if it were measured out per year. However, we're actually paying this amount on a compounded monthly basis. That means they're actually adding that monthly interest each month rather than waiting for the end of the year. So let's work this out here. If we have amount of interest that is 6% per year, that's equal to 6% divided by 12 per month, or 0.5% per month. So remember that percent means per 100 or divided by 100. So 1/2 we can think of as 0.5. So we have a 0.5% monthly interest rate. And when we divide by 100, you move the decimal twice to the left. So as a decimal value, that is 0.005 per month. All right, let's use that for our next row's entry. So in our next row, at t equals not 1 year, but 1 month, which would be 1/12 of a year, the amount of the value of the investment is 2,000 plus that 0.5% of 2,000. So that's going to be 2,000 times 0.005. Now that's a kind of a complicated expression, so let's do some factoring with this. You'll notice that both of the terms in that expression have a common factor of 2,000. That means that you can factor the 2,000 out, and you have 1 plus 0.005 left. Or, if we go ahead and add the things in the parentheses together, we have 2,000 times 1.005. So when we add that 0.5% to 2,000, we actually are just multiplying that 2,000 times 1.005. All right, let's make a third column entry. At 2 months, or 2/12 of a year, the amount of money that we'll have in that account will be 2,000 times 1.005 times another 1.005. At the end of 3 months, or 3/12 of a year, we would have $2,000 times 1.005 raised to the third power. So now let's generalize. V, the value of the investment, equals 2,000 times 1.005 raised to the, and what we'll want to notice about the relationship between the t values and the exponents is that those exponents are larger than the t values. They're larger than the t values by a factor of 12, so that means that the exponent will be 12 times the value of t. You recognize that 12 comes from the fact that we're compounding monthly, on a monthly basis. Important to remember that you have to deal with the annual interest rate, and then if it's compounded monthly, you need to figure out a monthly interest rate by dividing by 12. All right, there are a few for you to try here. So try A below and pause the video while you try this one. This one is a 4% per year, but there's no compounding involved, so it's just once a year. Okay, this one gave us an exponential function, and for this exponential function, the base is 1.04. Think of that as 104%. That is to say, after every year passes, the sales are 104% of what they initially were. All right, now try B. It's a very similar problem, but in this one, pay attention to the fact that the car is initially worth $35,000, but it is losing value or depreciating, as cars typically do. So pause the video while you try this one. Here's the function for this one. So when the car loses 18% of its value per year, you can think of this as what's left after you lose 18%. If you have 100% to begin with and you lose 18%, there's 82% left at the end of each year. So that becomes our base for this exponential function. All right, in C, this is one for you to try, and this one is one with compounding. So there's an 8% annual interest rate, but the compounding is happening quarterly. Quarterly means 4 times a year, so think about what your quarterly interest rate would be. Try this one and pause the video. So for C, our quarterly interest rate is 2%. So that means at the end of each quarter of a year, the investment gets multiplied by 102%, or 1.02. So the function is V equals 65,000 times 1.02 raised to the 4t power. All right, in example 3, we're going to set this up and we're going to then use our solving to actually solve some problems, use our tools to solve exponential equations. And so for this one, we're going to use our calculator for a final answer. In example 3, we'll do another half-life problem. The half-life of a radioactive element is 4 days. So let's start by creating a table of values. So T is time measured in days, and A is the amount of radioactive material present. So at T equals 0 days, the initial time, there are 3.2 grams of the element present. After 4 days, or 1 half-life, that amount gets multiplied by 1/2. After another 4 days, so at 8 days, that amount, 3.2, gets multiplied by 1/2 one more time, so we're now multiplying by 1/2 squared. And after another 4 days, or 12 days, 3.2 gets multiplied by 1/2 raised to the third power. So what you'll notice here is that our exponents are smaller than the time values. In fact, they're smaller by a factor of 4. So the exponent is the time value divided by 4. So there's our model that we're going to use. Okay, in part B, we are asked how much of the element remains 5 days after the start of the experiment. So that means that when they ask how much of the element, that's actually, I wrote that variable wrong. Let me go back to part A. That should have been A equals 3.2 times 1/2 to the t over 4. And so when they say how much of the element is left, they're asking for the value of A. And they tell us that their t is equal to 5 days. So that means we are just going to replace t with the number 5 in that model. And then there's no solving to do. We're just going to put the expression on the right side of the equation into the calculator, and we'll get a decimal value for A. So A's value is, we're going to pick up the calculator here. Let me move the calculator into the screen. And so we need to enter from the home screen. We can grab a scratch pad and enter 3.2 times, I'll use parentheses, 1/2 raised to the 5/4 power. And we get 1.345. And 1.345 would be measured in grams. In C, they ask us a different type of question. After how many days are only 0.1 gram of the radioactive element remaining? So this time they are looking for the value of t. So t equals what? When A, the amount is 0.1 gram. So this time we'll replace A with 0.1, and we'll leave t in the equation to be solved for. So this is an exponential function. We can solve it by putting this in a logarithmic form, but before we put it in a logarithmic form, we need to have that exponential expression isolated. That means 3.2 needs to go away on the right side of the equation. So I'm going to divide both sides by 3.2. And 0.1 divided by 3.2 is the same as 1/32. You can leave it as 0.1 over 3.2 if you wish. It's not going to matter for our final answer. And then we're going to put this in logarithmic form. So what that means is the log base 1/2 of 1/32 equals the exponent t over 4. So that means that t over 4, or rather, I'm sorry, that means that t is equal to 4 times the log base 1/2 of 1/32. And now we can just enter that value into the calculator. So in order to enter a log, I'll go ahead and enter that 4. We can enter multiplication here or not, doesn't matter. The calculator will understand if we just smush them together. So 4 times the log, and to get log, control and the 10 to the x button. Now put in the base 1/2, and then cursor over, put 1/32 inside of the log, and just enter. And that's going to give us 20. And since that was a value of t, it's going to be 20 days. All right, let's take a look at a money problem. Now for this one, we're actually not having to develop the model For this, I'm actually giving you the model here. So if P dollars is deposited into a savings account and no money's withdrawn, and this time the annual interest rate is 0.6%, but the amount of interest is rather compounded continuously. This calls for a very specific model. A is equal to P times E raised to the interest rate as a decimal times T. So for an initial deposit of 3,000, that's the value of P. How much money would be in the account? That's the value of A. So we're looking at A is equal to I don't know what. After 10 years, that's the value of T. So we have T, we have P, we're looking for A. So A is equal to 3,000 times E raised to the 0.006 times 10. Again, no solving to do on this one. This is, since we're looking for A, we just have to enter the stuff on the right side of the equation into the calculator. All right, so let's grab that. If you don't like the messy calculator screen, you can use menu 1-5 to clear it, and then just enter in 3,000. And then we're going to enter in E raised to the. Now remember not to use the alpha E, just use the E to the X button. And you'll see that E is bolded. Don't worry if you try to use the alpha key by mistake, the calculator will yell at you. It'll tell you it doesn't know what you mean, and that's okay. You'll just know that you have to use that E to the X button. So E raised to the 0.006 times 10. Enter. And that gives us, remember this is a dollar amount, right? So $31.85, but typically you don't see three digits after the decimal point for a dollar. You just see 2 digits, so it can have dollars and cents. So $31.85 and 51 cents. So whenever you have money, round to 2 digits after the decimal point. All right, in B, it asks us how long it takes for that money in the account to double in value. So how long means we're looking for the value of T. And our initial deposit is doubling in value. So that means that A, the amount in the account, will now be 6,000. So 6,000 is equal to 3,000 times E raised to the 0.006 times T, and now we need to solve for T. Now remember, this is a very, very small interest rate, so the answer will probably be something that's disappointing. We need to isolate that exponential function. We can do so by dividing by 3,000. That'll leave us with 2 is equal to E to the 0.006 times T. Since this is a base E exponential expression, when we solve for the exponent, we're going to put it in a natural log format. So natural log of 2 is equal to the exponent 0.006 times T. And we can solve for T by dividing the natural log of 2 by 0.006. Now all that's left is for us to put this in the calculator. So natural log is control E to the X. So natural log of 2, cursor outside of that parenthesis, and then divide by 0.006. Enter. And this is 115.525 years. So at that interest rate, I really don't hope to double my value in my lifetime. All right, let's go on to another model. This is what's called a logistics growth model, and it could be used for the spread of a rumor. It can also be used for the spread of infectious disease. It actually is a model that's used by epidemiologists. And in this model, we're just spreading a rumor, or we're talking about the spread of a rumor. S is the number of students in the upper school who have heard a rumor after T hours. And S is equal to 440 over 1 plus 87e to the negative 0.9t. So we're asked how many people knew the rumor initially. So initially means when t is equal to 0. So S, the number of people, is equal to 440 over 1 plus 87 e to the negative 0.9 times 0. Now, again, we don't have to solve for, we just have to enter that value into the calculator. Let me clear that screen again, menu 1.5, and we'll want to use control divide for horizontal fraction bar. 440 goes on top of the fraction, cursor down to get the into the denominator. 1 plus 87 e to the negative, and when you're entering a negative, be careful that you don't use the minus sign. Use the negative 0.9 times 0, and just enter, and it turns out that 5 people knew that rumor at the start. And next, we're asked how many people know the rumor after 8, 10, and 12 hours. Well, this is a really similar question, so I'm not going to write down the calculation each time, but we'll just alter the calculation that we did in part A on the calculator. And so remember that the way that you can do this on the calculator is to go ahead and use the cursor up button to grab that calculation again. Once it's highlighted, press enter, and then backtrack using your cursor, and then just delete that 0 and replace it with t equals 8. And apparently after 8 hours, 413 people knew. Now, rounding, we're talking about a number of people here, right? So it doesn't make sense for us to round this value to the nearest thousandth. We wouldn't say at the end of 8 hours, 413.164 people knew. We would round it to 413. All right, let's grab that value for t equals 10. So again, cursor up, grab that calculation, press enter, then use your arrow keys to find that 8, delete it, and change it to 10. So at the end of 10 hours, it appears that the spread rate is slowing, which makes sense, right? Because there's only 440 people in the upper school. So once the majority of them know, it's going to spread more slowly to the rest. These people might be absent or in the library or not paying attention. I don't know what's happening. Let's check out what's happening at t equals 12, because by then, hopefully most of the upper school knows this rumor. And 439 people know. I guess that 440th person is, I don't know what's happening with that person. You can use your imagination. All right. And in part C, it asks us if there's 440 students in the upper school, how long does it take for half the student body to hear the rumor? So we know that at t equals 8, more than half knew, right? So it's going to be a smaller number than that. So let's remember what our equation was. It was 440 over 1 plus 87 e to the negative 0.9 times t. And half of the student body would be 220 students. So we'll just replace s with that number. And in order to solve this one, I would suggest that it's going to be easiest to just clear the fraction from the equation first. So we'll multiply by that big old denominator, 1 plus 87 e to the negative 0.9 t. So we have 220 times that quantity. And I'm going to suggest that a real easy way for us to solve this one would be to, at this point, divide by 220. That's just going to give us 1 plus 87 e to the negative 0.9 t is equal to 2. Subtract off the 1 and divide by 87, and now we have our exponential expression isolated, that means we're now good to write this in logarithmic form. Since it's base e, it's going to be a natural logarithm. So the natural logarithm of 1/87th is equal to the exponent negative 0.9t. We can now divide through by negative 0.9. And we're ready for a decimal value. Let's move our calculator over here. Menu 1.5, I'll clear the screen, and we have a value of ln, so that's control and e to the x, 1/87th. Cursor over so you're outside of the parentheses, divided by negative 0.9. Enter, and that's at the end of, what was that, 4.962? So 4.962, and that time was measured in hours for this problem. So it takes about 5 hours for half the student body to know, according to this model. Well, that's it for this lesson and for this unit.